When we're talking about the half-life of a material, we're talking about the rate at which the radioactive material will decay into a stable state. However, that's not all. It's really only talking about half of that material decaying into a stable state. And that rate could be from milliseconds to billions of years. It is also a rate, but it's also a probability. It only generally works with larger quantities. It doesn't generally work with, let's say, a single atom. However, it being a probability compared to a rate is not really a problem. When we have a single gram worth of a material, it has large quantities of atoms in it. So the rate still works. However, if we only had one atom, the probability of calculating it is not accurate at all. So how do we calculate our half-life? Well, luckily, you may have some equations that we can work with. From mathematics, you should have seen an equation that looks something similar to this, where A0 is our sample originally, our T is the time, and that can be in seconds or millions of years. Our lambda in here is our decay constant, and this A over here is the remaining amount. For this equation, we need to know our decay constant, which you may not always get in every single question. For that, we have another equation to deal with. This one is just A is equal to A0, 1/2 to the power of n. Our A0 is still the same, so this is our original amount. Our A is our remaining sample. Half here refers to, well, it's decaying by half that amount. And the n here refers to the number of half-lives. Depending on the situation, either of these questions could work, but you have to read the information that you're given. If you're given a decay constant, this equation over here is probably going to give you a better answer. However, not all questions will have a decay constant, so this equation here would be the one to use.